Mm-hmm. I see. Mm-hmm. Doesn't that not work? I don't know why all these problems are so interested in sums of digits, but in this case, seemingly this wouldn't work. If I have, well, it doesn't say that the numbers are uniquely grouped. But okay, if I have 111, then I have 3. Or rather, if I have 110, I have 2. If I have 120, I have 3. I mean, seemingly the answer to this is n minus the number of integers. No, that's not right. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So you would. Hmm. I feel like this isn't enough information because what do we do when we hit 10? Well, yeah, specifically, what do we do in the next step? Well, no, that's not quite right because it would be 15. Let's carry this over here. Okay, so so if I had 5, 14, 6, 15, 7, 18, 8, 19. Wait, hold on. We got misplaced somewhere around here. 16. There we go. 8, 17. 9, 18. Yeah, well, we don't have any evidence of what this problem expects. We don't have any examples of what this problem expects when you have when you wrap back around. Because this process doesn't, so you have 10, 11, 12, 13, but 13 was the max value in this example, n equals 13. So you don't have an example of what happens after that. Yeah, but that's also not quite the point, I think. The point is what happens at this. After this juncture where we have 10 and 19. And now the point is also that we have number in second position, number in first position. Alright, I'm going to take a hint because this is not making much sense to me. Okay, I mean, this might just, it might actually just be, let's see, if less than n10, n, otherwise minus n 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Count largest group. I might have to do some plus minusing here. 4, that is correct. 2 is correct. Looks like we don't need to do any plus minusing. Okay, well, this is a 68.9% acceptance rate. Where they're gonna flip it over, flip it up or flip it down. There's not an additional source of information here outside of simply looking at the answers, so Huh. Okay, well, I guess we'll do it up to 24 and see what we're supposed to do. So here's the first case where we have this. So that, I'm guessing, is the point, that this turns into 1, 10, 19. And then 2, 11, 20, 3, 12, 21, 4, 13, 22, 5, 14, 23. No, that's not it. Because then... 13 inclusive. If we move up to 24, we would have 6, 15, 24, which is 6 samples. Okay, so this is not a case, apparently, where you don't have to continue collapsing these, but then this doesn't make any sense. There's an inclination here to say, what is this problem even talking about? What a malformed problem. It's like I'm trying to offload my sense of embarrassment at not seeing the answer onto the question. Or the question designer. Though it's true, I don't see the point of this problem. Yet. Yeah, I'm not sure thinking is going to do anything here. there are 4 groups. No, hold on, wrong answer. Over here, there are expected 5 from 24. This interpretation produces 6. Hmm. Alright. I don't think continuing to look at this is going to yield an answer. Um... What? I still don't get this. Is this the idea? No, that's not the idea. Presumably. Has anybody solved this in Racket? Yes. What is this talking about? Uh-huh. So there's this point that my eyes are only used to traversing code that is in the shape that I use. And I feel like there's a deep point to be made there, but I'm not trying to make a deep point at the moment. Merely want to observe this phenomenon that you, if you have a disordered desk but you are intimately familiar with the distribution of contents on your desk, it no longer looks disorderly. Disorder is relative to some conception of order. Okay. So my code looks orderly to me because that's what my conception of order is. But on the other hand, I think we can all agree that my code is more orderly and comprehensible than anybody else who writes Racket that we have seen up to this point. Notwithstanding that we are biased in this evaluation by the fact that we can't read anything else, or have only tried reading my own code. This naked let. Alright, let's see here. Let rec count largest lambda lengths. Not a plain lambda, already losing efficiency. Let loop lens. Oh, lens is lengths. Okay. Let me define longest zero, count 0. Right, empty lens return count. hold on, do we have... What calls count largest? Down here, this is the procedure call. This is probably the place where we should be starting. If so, let me think here. We have let loop num is 1 groups. Okay, so we're gonna have a hash table. An immutable hash table. If num greater than n, count largest map length to hash values groups. So this let definition is a procedure. It just grates against my eyes because it doesn't have a parent out front. I don't use this form. Anyway, if greater than num n, count largest map length hash values groups. Okay. So count largest, which is this up here, is going to be receiving a mapping of length to hash values. Okay, hash values returns a list. That's all the values of a hash table. So we're taking the length. So this anticipates that these groups are going to be lists, or else we wouldn't be able to run length, which is the list length, on them. So we're mapping length to hash values. Okay, what are we putting into our hash table? Well, so this is a loop. It's when num is greater than n. So this is num and n is the provided value. So I assume we're incrementing, add 1, yeah. Alright, so if greater than num n, then count largest, otherwise let star some digits num, some digits being... Yeah, we can run a test to see whether it's better to make string than read the string, or this, given our ability to make a string and then read the string. But this, one way or another, this is going to sum the digits fine. So some digits num. So we're on a current number. That is incrementing in each step. Okay. Let's do a little bit more formatting. Okay. And then nums hashref groups sum false. This is the name of our hash table. This is the sum we've just arrived at. Yeah, no, that's not it though, right? Because... let me think here. Okay, I'm not sure yet. Under what condition are we hashing? So we're hash refing the sum of our digits. Okay. If nums. Yeah, so this is where we would want to do if hash has key. Then we add hash ref otherwise, I think, but I'll ignore that for now. So if nums loop add 1 to num and we hash set constant num onto nums, and then otherwise if there is no current list, we create list num. So what is num here? Is the current state of this value. We stop if num is greater than n. Okay. This is producing a list. We're consting num onto nums, where nums is the return from the hash table. Okay, but that doesn't make any sense either, though, right? Because no, never mind. That doesn't. That's not a counter argument. Let's see. So we have the hash ref, which returns sum. No. Sum is running some digits on num. So we sum up the digits of our current number. We're recycling through that number. We run hash ref on that sum value. Okay, and that brings back either a list or actually you instead of having an if here, you could return null and always do const num incidentally. Let me see. So I const num onto the list of numbers that have had that sum of digits. Okay, let me ask a quick question here. What does this think is the answer to 24? Okay, correctly returns 5. Show me... That's because we added this one in erroneously. "19 sums to 10, not 1. It's not like a cascade. Though then, it's odd that this doesn't include... Why does 19 not have 10? What happens if I use input of 19? So that seems broken, right? And in this case, it would explicitly return an incorrect value. Supposing this is wrong, this would give me the incorrect value because this should give 10. Or is there something I don't understand about the rules yet that say... something I don't understand about the rules that tells me that this is supposed to be unpaired? Okay, and then we go through, and this asks, let's see, what is this called with? Map length onto hash values. Okay, so we turn all these lists into a list of lengths. And this is just a confusing, well, confusing because of its layout way of, confusing to me way of counting the maximum number. Or the way of counting the length that has the maximum corresponding number of instances. Okay, Wait, so why is the 19 not getting grouped up? Yeah, I mean we get 19 and 10. It's also it's the first instance of the sum being 10. Okay, so now if we come down here, oh, well that's it. That's the point actually. It's the first case where the sum is not equal to an earlier single digit number. And that's actually all the mystery there is. So there isn't another number with the sum of digits that's equal to 10. Which is confusing, if at all, because again, each preceding number has had a sum of digits that was equal to a one-digit number and therefore got a free pairing. This doesn't get a pairing because 10 is not a one-digit number. Okay. Okay, let's see here. Well, yeah, we don't know what the... Yeah, but it's all... Well, do we want it to be modular? What do I mean? Sum of digits. Some digits. Do we want this to be modular? Which is to say that we could map some digits instead of doing both at the same time. So this does both the hashing and the summing of digits. We could map the summing of digits and then, but then it would still be. It would still be modular. I guess the point would be that you don't have to have a separate function. You could do this. Actually, how does this sum digits work? If less than A10, then return A. Okay, otherwise plus modulo A10. And then, okay, so it does loop back on itself. Let's see, if I were to do this, let's see. Let me think. Quotient and remainder. No. Let me think. How would this be useful? So we have. Right, well, if I have. Yeah, or 555. Yeah, so the point about modularity here, we could figure out later which is faster. We could also figure it out now. It's not such a big problem. List generator. Alright, so we need to design our. Alright, so my quotient remainder solution. Define QR cycle function. Quotient remainder function. QR sum function, sure. Alright, so we have n integer and we have accumulator integer. Alright, so now I'm going to say let values. How does that work? Do I need a let definition? Yeah, well, if I'm going to use quotient remainder, yes. Let's see. If less than an integer, we could do less than an integer 1. No, that doesn't work because you would get, yeah, okay, less than an integer 10. Alright, we'll say quotient. Wait, how does the syntax work for this? is this? It's triple wrapped. Nope. There we go. Alright, so this is one option. The other option is to use strings, which doesn't involve division, which is regularly a boon for efficiency. You want to avoid division if it is possible to do so. Okay, so how do we do strings? So let's see. Define the string sum function. Input string. Alright, fold L. Let me see. This is going to be horrible. Fold L. Well, actually, we could do. Maybe we can make this less horrible. Plus 0 on /list. This is not getting less horrible. Let me see here. So we need to. Map /list. So let me see here. So this specifically showed me using a string as here, yeah, /list. Okay, this is gonna get real horrible. QA input string. No, there. Yeah, input string. And then simply return I. Okay, and what we are mapping onto that is so we could fold left twice. Fold L. This is the input list. Fold L lambda char minus char to integer. Char to integer char 48. this thing under result null operating on /list. Okay. Maybe that works. If that works, first try. Yep, yeah, okay. Let's see. Well, it wouldn't be a string, would it? Oh. Oops. Okay, well that works. Astonishingly. Alright. Alright, what are the constraints in our number here? 10 to the 4, which we need not look it up, but you know, okay, 10,000. Alright, so my list generator will have range 10,001. Okay, and now we will run time on, let me see. So QR sum. Okay, time map QR sum function. Actually, so we have two interesting related tests here, though the second test that just came to mind we could do at any time. We could test whether map is simply faster than fold L in all cases. Well, rather for putting a sequence of numbers into a list. The idea being fold L should be faster because we don't care about order, whereas map has to do something to retain order. Map lambda integer QR sum function integer. Yeah, I mean if we make accumulator integer a default value, then we can forego our lambda expression and simply say map QR sum function. I'm guessing this is going to end up being faster because the process, we're going to have to do mapping or fold lefting, stringifying. We're going to have to turn every element into a string for the other function, which I think is going to impose a cost. Map QR sum function onto a and then this thing. So I do time map lambda integer plain lambda, please. Map plain lambda. Speaking of which, we'll take plain lambda here as well. Plain lambda only, please. Alright, so map plain lambda integer onto rather plain lambda integer with the function being string sum function on tilde a integer. And we're running that on a. Okay, go. $156. Oh no, it just keeps getting longer. Oh no. 300. 200. Widely varying. 230. Alright, let's see what this gives me. 46. Yeah. Strings are horrible. Horrible, horrible, horrible. Alright, so this is definitely the better approach. Now I want to ask a related question. What do I get if I fold left instead of mapping? And if it's not faster, I'm displeased. Wait, no, keep that. I think we'll get rid of that. I'm pleased that that procedure worked. It's just not a good procedure. It's, not good. Alright. And actually, we could also run a speed test on this person's. We could just take the best. But here, we're going to run fold L instead. Now, part of the problem here is that we have to do a lambda. Now, though, the payoff is that we don't have to reverse. It's much slower, really. It's like 3 times slower. Still slower. Yeah, it's because we're getting hit with a garbage collection cycle. But even then, even when you don't get hit with garbage collection, still 46 as opposed to 31. Actually, here's a question. If I define B null, okay. And now, instead of outputting this value, I say set B const. Okay, and now I don't have to perform this lambda. I don't have to reference. I don't have to perform a const. I don't have to have result. I don't have to reference integer. Okay. And so actually this is just for each. Alright, what if I insist on fold L? Well, okay. Wait, what is that gonna do? Okay, fine, for each. So that's also 31. Alright, and now let's do a time test on the opponent's function. Some digits. Okay. So we want to map some digits onto A. Okay, define some digits. Input integer. Wait, what? Hold on. How does this... Oh, it's a non-tail recursive. If. How do you get this to interact with... Well, what was the problem? What was the error? Albeit these are impossible to read. Unbelievable. Yeah, okay. Yeah, well, the promise that using quotient remainder would give us a better output did not live up to expectations. Yeah. Alright. Can we do anything to make this more efficient? Well, we might be winning on memory at any rate, if not on execution speed. But how? So we put this off to the side, or we map this first. So that would be the next test. Is if we map this function onto. Let me think. We map this function onto the integers from 1 to n. And then we perform the hashing. Okay. An alternative question would be to ask, Is there any pattern in the sums of digits? We could try doing some number theory. Is there a pattern in the sum of digits? Well, we could implement this first and then figure that out. Though actually, yeah, we could take this function, map it to map qr sum function onto range 1000. Is there a pattern? Yes, there is a pattern. A closed form solution, if you will. 0 through 9, nope, 0 through 10. But wait, why is it 0 through 10? Also, why does it start at 0 if I do range? Actually, we could do this directly here. Range. Apparently it starts at 0. Huh. Okay. Why does it go up to... It doesn't go up to 10. Oh, we got confused. We saw 20 consecutive digits and thought it was 10. Yeah, well, whatever. So we have 0 through 9, then we have 1 through 10, then we have 2 through 11, 3 through 12, 4 through 13. Okay. Yeah, but what does this actually tell me? I'm still having a hard time understanding that, but it's the number of numbers that have the same sum of digits. So that's going to max out. What do I mean? So discarding the 0, we have 1 through 9, then we have 1 through 10. And then we have 2 through 11. So the number of cases where the sum of digits is equal to 1. No, it's going to loop back around. This process resets at some point. Let's see. Well, yes, it resets, doesn't it, at here. How about we do in integer? What is the efficient way of doing this? We want the element that's being we want the element, the digits of which are being summed, to be const onto, so that we can see what it is that we're summing up. map plain lambda integer range const range integer onto yeah, I'm afraid that's not actually the most efficient way to do this. I don't like that I'm specifically calling the function. I don't like I don't like that I had to have a lambda expression. That makes me worried about the efficiency of this call. Three to 12, 4 to 13. So when we hit 100, we loop back around to 1, and the same thing is going to happen at 1,000. It's interesting that 9 stops 1 short of 10, 18, which is the sum of 9, 9, stops 2 short of 20. 27, which is 999, will stop 3 short of 30. So the gap between this grows. The gap between this and the next 10's value grows. Now we repeat the cycle, once again starting at 1, but interestingly here we go all the way up to 10. And let's think about the corresponding case. If we had 1009, that would also be 10, but then we would have 1010, which would be 11 instead of 110, which is 2. So now we have 2 to 11, 3 to 12. We do 2000. So 1000 starts at 1 and goes up to 10, then we have 2 to 11. Whereas if we go back to just post 100, 1 to 10, 2 to 11. Okay, 12, 17, that's weird. So we have 169, which is 16, 159 is 15, then 16, oh there it is, 17, I thought we skipped one. That would be strange. Wait, we did we skip? No, 18 here. It's visually confusing because instead of going back to a single digit number, you go back to 10, which is a 2-digit number, which wasn't the case in any of these. Yeah, okay, so 10. to 19. And then at 200 we wrap around to 2. So, how do we work this into a solution? Hmm. One to 9. Then 1 to 10. 2 to 11. I guess we include 0 in this because otherwise... Yeah, but, yeah, I don't know. It keeps the format the same so that we'd be saying you have 3, 6, 9, 10 numbers per group, which remains correct. Yeah, okay, sure. We have 0 through 9, albeit in the actual case that 1 is cut off, or the 0 rather is cut off. But okay, so we have 0 through 9, so 10 elements in a row. 1 through 10, 2 through 11, so each of these is going to be 10. 3, 6, 9, 10. 3 to 12. Alright, so this continues all the way up to... Where does this continue all the way up to? 4 to 13, 5 to 14, 6 to 15, 7 to 16, 8 to 17, 9 to 18. So let's, for instance, track this 9. So we have 9, 9, 9. Okay, and eventually that's going to be the first. Or we're going to encounter the first introduction of 9, which is down here. So within each cluster of 100, within the first 100, if we continue all the way through 100, we're going to get how many copies? Well, let's track 11. Also, we can do that with find. So track 11 on the right side. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, we already passed it. 8. And so 10 we would have had 9 copies of. So within the first 100 we have 10 copies of 9, 9 copies of 10, 8 copies of 11. And then presumably 7 copies of 12, 6 copies of 13, etc. Okay. Zero copies of 19. Strangely, we would get the first copy of 19 right before 200. We get 2 copies of 18. By the time we complete 200. Okay. Let me ask again. What is this asking for? They're groups of size 1. Okay, and in this case, groups of 4 groups of the largest size. It'd be more convenient if we were returning the largest size, because that's on this kind of loop. Well, the number of groups with the largest size is also in this loop. What time is it? We need to stand up and do exercise soon. I guess this is what a lot of well, I don't know. We would have to study it, but I'm guessing some of number theory is going to look like this, and I actually have some fun engaging in this. Alright. Stand up. Oh, I'm gonna get a lot of joy out of. I'm gonna get a lot of joy out of plain lambda. I need to hard code I need to set up my IDE so that plain lambda is printed out in rainbow colors. Plain lambda. Alright, I'll bear it back and then I will do exercise. Okay. I don't mean to seem like I care about dear things. I just want for all the things I wanna do. I don't mean to seem like I care about dear things. On social status. I just want for all the things for a girl. I don't mean to seem like I care about dear things. This weight on the bottom of the hilt idea for an S-stock. It would already be a heavy weapon. Yes, you'd have to be quite strong. Though you'd be two-handing it, which makes it easier, I think. You know, you're not... Well, then you have just the absolute ox who uses a shield in the weighted S-stock. Well, and I mean... yeah, I mean, you have, if we were talking about one of these Souls games, you have people using Guts' sword from Berserk, so if you had a weighted S-stock, that's not so unrealistic, right? Weighted S-stock and shield. It's not internally relatively unrealistic anyway. Actually, so I never got back around to the point I was trying to make, or the point I started to make yesterday during the exercise and talking out loud segment. So my initial point was actually that you start out carefully attending your muscles, dodging the pain muscle. There's a pain muscle you don't want to activate, but you still want to exercise the upper body, apparently. Okay, so you're carefully attending, making sure you're not activating the pain muscle. Now, what is the idea? Well, so you give yourself a kind of characterization, or you have this simplification. You have this rule that you take yourself to be following. Okay, and it replaces the avoid the pain muscle rule. I mean, the rule, instead of, like, I choose this motion because it avoids the pain muscle at first, and then I choose this motion because I've already chosen it. And then I choose it even though it activates the pain muscle later. And I'm not paying enough attention, and I've activated the pain muscle, which I wanted to avoid. Letting an activity become rote is what we're trying to avoid, I guess. Yeah, I'm excited. I'm excited to jump on the AI bandwagon that I'm currently considering. I have to get a credit card first, but I feel like we have image software that can produce, we have image models that can produce images that meet any description you desire. And yet it does not appear that anyone has tried using image models to produce diagrams, for instance, that meet specifications. Working with models to produce diagrams. I want a windswept, snowy gingerbread house. I want aurora in the sky, and I want a cloud of fireflies. I want a pretty lady with orange hair and just these thick lips. Yeah, that's what I want in my image. No, you want the point of the image model is to replace the need for artistic ability, right? But the need for artistic ability has abounded. It's all over the place. You need artistic ability when designing diagrams, for instance. Or else your diagram is going to look bad. You're going to choose the wrong colors. And when you realize that there's an effect that you want your diagram to have, you're not going to know how to give your diagram that effect. How do I make these matte? What is the matte effect? M-A-T-T-E. What is that even? I don't know. I don't know what you do to colors to make them matte. The image model knows what you do. I don't. But I want matte colors for my diagram. Well, you better have the image model then. I don't know. So I'm gonna have to drop into the bank like Andy Dufresne at the end of Shawshank Redemption. Mathematical Society membership. I'm officially going to become a mathematician by joining the Mathematical Society. Oh, how the world would be different if the American Mathematical Society was the largest private organization with billions in funding. Anyway. So now, yes, the question is, how do we turn this pile of observations about the behavior of digit sums into actionable code, actionable observations? Side point, I think people are unduly afraid of repeating words. It's like one of the few stylistic pointers you get. It gets hammered in. Don't repeat words. If you find yourself repeating a word, pull out a thesaurus and use a word you've never used before instead. And it's bad advice. Just reuse the word. Sometimes. Anyway, let me see here. $179.17, 169.16, 159.15. Right, and you have to, again, it would, if it was asking what is the largest group size, we could divide this up into intervals. Right, yeah, well, I mean, yeah, what is the size of the largest group? We could divide it up into intervals, because that's going to follow the pattern. Really, at any rate, all we need to do is track 1. No, not 1, actually. Well, okay, let's, even if I can't solve this, we can at least do exercises. What do I mean? So, define a... let's see if there's something we can do with this. Well, so it turns out that 1 is not going to be the best sum. Actually, no, 1 is... Yeah, well, because we get 1 from 1, then we get 1 from 10. And then we don't get another 1 until 100. Whereas we get 9 from 9, we get 9 from 18, we get 9 from 27. So it turns out that 9 is going to be the most proliferous out of the first 100. Let's see, count. Yeah, we can run count operations on this, if nothing else. I mean, we could do full 10,000 and just say electricity here is free. Electricity at point of operation is expensive. So, count lambda pair equals CDR pair 9 running on A. 220. Okay, similarly, we don't have to be intentionally inefficient. But I mean, on the other hand, this is what immediately struck me. I don't. Well, I mean, but so yes, this is the routing that immediately strikes me for determining how many elements have some of these have a digit sum of these values. Okay, but the ideal is that you develop your skill enough so that what immediately strikes you is good. This is not good. This is sub-ideal, I would say, but okay, whatever. Well, I mean, and the point is, like, my examinations are halting and stumbling, and you'd say, just, you know, you already see a solution, why are you pausing and figuring out the better solution? Just perform the investigation, but the point is that you refine your inclinations through declining to follow through on your inclinations. Anyway, 4 to 10 is 6, 10 to 20 is 10. So 6, 10, 15, that sounds familiar. 21. 6 is 1 plus 2 plus 3. Plus 4, plus 5, plus 6. So rather, if we lay out these numbers, let's exit that. Okay, yeah, but then we need, actually, I'm gonna just get rid of that, because that was not useful note-taking. Don't need this. Hide my embarrassment that I lost a time test. Don't need that. I drew a time test that I should have won. Don't need that. Keep that open for now. Don't need that. And we have no copies of, here. Alright, now we'll close that, go back over here. Now we have these numbers. What do we want to do with these numbers? Alright, so this is 4 plus 1 plus 2 plus 3. This is 10 plus 1 plus 2 plus 3 plus 4. Yeah, and then 20 plus 1 plus 2 plus 3 plus 4 plus 5. The pattern continues. Uh, 15, 21, 26, 30, 33, 35, yep. Okay, and then a pattern here is that well, so this is the number of ones. This is the number of twos. This is the number of fours, number of fives, number of sixes, number of sevens, number of eights. down here we have the number of nines. And the point here is that 9 enters, well, in this paradigm, in this way of performing the analysis, yeah, we want A back. Oh, and this is 10,000. Well, and then that conveniently is also the range of the problem, not for nothing. Let me get this. Let me get this, and then this over here, and show me this again. Oh, this is all 10,000. Yeah, let's take 1,000 here. So 9 starts at the bottom. So we got our first copy of 9 at the end of the first sequence of 9. Then we got our second all the way up to 100, where we get our last copy of 9, which is the last one-digit number. Okay, then we get our first copy of 9 again, but now it's in the second position. Now 9 shifts up. 9 shifts up each time, so now there's 10, 11, 12, 13, 14, 15 on the other side of it. Now it's up to 16, now it's up to 17, now 9 is in its last position, and it's replaced by 10. So there were more copies of 10 in the second 100 than copies of 9, because we initially had 9, 10, and so 10 has been in every loop, every cycle. Yeah, probably want to mean something different by those words, but whatever. Okay, now 1 is cut out. There are going to be more copies of 11 than 10. And so on, all the way up to 1,000, where in the next 100 there are going to be more copies of 12 than 11, then there will be more copies of 13 than 12. Okay. If I do 1,000 to 2,000, now we're going to have, we start at 1 and go to 10. Okay. And that's for the first 100, there are going to be more 10s. So in the first 100, there will be more 9s than anything else. In the second 100, there will be more 10s than anything else. And that's in the first 1,000. In the second 1,000, in the first 100, there will be more 10s than anything else. In the second 100, there will be more 11s. So we shift. Okay, let's see. So 0 to 100. 100 to 99. Hold on, that. 100 to 199 will be 10. 100, 200 to 299 will be 11, dot, dot, dot. 900 to 999. So it's what is the pattern here? How do I succeed at the dot 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 skip? There's often a typographical rule you can follow to execute a dot 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 skip, but let's see here. That's like we're indexed to -1 relative to 10. So this is 100, then we ask how many 100s are we above 100? We're 100 above 100. Here we are 8 100s above 100. We can also count with our fingers. 1 to 10, 2 to 11, 3 to 12, 4 to 13, but it's always one less. Yeah, so there's our typographical rule. All right. So now when we do 1000 to 1099, we will have the most frequent number is 10. Okay, and then 1100 to 1000, rather, yeah, okay, well, sure, 1199 will be 11, and then I'll execute the dot 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 skip, and then we have 1900 to 1999, which is, so now we're on numbers, so this will be 19. Okay. I think this is obscuring. Let me get rid of some of these. So 9 to 18, 10 to 19. Okay, and then we execute another dot 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 skip. And now this will be 9,900. Actually, let's do 9,000 to 9,099. Interesting. What is that going to be? So it's going to increment. Well, hold on. So we jumped here from 9 to 10. Okay, 10. The next one would be 11. And that would be for 2,000. So it's this digit. This digit is the number of thousands. String math. Yeah, it's string math. This digit is the number of thousands we are above 1,000 with some kind of special accounting for 9. Okay, the number of digits we are above 1,000. Rather, what? This digit tells us the number of thousands we are above 1,000. We are 0 thousands above 1,000. Alright. We are 8 1,000s above 1,000. Okay. Huh. Though then there's some, well, it would, I guess it would be immediately after this. 2,000 would start with 20. Yeah, okay. And now we do alright, now typographical rule. We are 8 above the hundreds place. 9, no, we're always 8 above the hundreds place. Okay, so if the hundreds place is, then this is going to be 8 above, so 17. 27, rather. Okay. This is telling me the maximal number per 100, or per... Okay, yeah, per 100. Now what is the idea? So this is the most instances, during this 100 we will have the most instances of 18, during this 100 we will have the most instances of 19, during this 100 we'll have the most instances of 27 as the sum of digits. Okay, now what do we do with that? How many are there? Does that matter yet? That's for the full 10,000. If we wanted specifically for 1,000, we could recalculate. 55. Okay. And if I did 9,000, rather range 9,000, 10,001, and I instead asked count 27. Also 55. Okay, so... yeah, so actually we should have saved that oh, we did save that calculation, didn't we? Where am I? Yes, we saved this. So, wait, 56? Alright. Let's pay a penny. Okay. Well, yeah, if we do 1,000. Yeah, though, it's the recalculation on the counting that's the problem, but whatever. 55. Why is it 55? Oh, yeah, I guess we're getting confused because this is the sum from... This is the number from 0 to 10,000. Okay. Let me think here. So we have 55 copies of this number. So can I do like that? No. Kind of. Yeah, but that doesn't actually solve the problem. Hold on. If we put the parent here... Trying vainly to incorporate pretty printing into text editing. Yeah. Right. So 55. Right, well it's going to be 55 for each of these because we're only asking what is the most proliferous number within a 100 range, and it's going to be the same each time. So there are going to be 55 copies of numbers, or there are going to be 55 numbers that sum to 9. 55, really? Well, no, actually, that's in the first 1,000. Oh yeah, then that's not the question we're looking for here, I think. If anything, we're asking about 100. Well, you know, we could, yeah, well. Yeah, let's do 100. Two, three, four, five, six, seven, eight, nine, 10. A different pattern, I guess we could have, well, a different pattern here. And what is this different pattern telling us? It is telling us that we have 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be the answer for each range. This is going to be the answer for the most proliferous. Let me think here. Well, so there's also an answer for 10, right? What is that? Ah, I see, it goes back down. Seems like there's really no reason that would be the case, and yet here we are. Again, I have no reason to suspect that it would go back down like this, but now that I'm thinking about it, of course it would go back down like this. It's like the grammar makes it happen, as it were. Okay, so we peak here at 9. I guess we didn't ask 1. No, we didn't ask 0. Which would be 1 because the number 0 is included in this range. Okay, now, so this is going to remain consistent. Okay, so for 0 to 99, we're going to have 1, do this. Can I just do down? Yeah. What? Where did I go? Okay, get rid of the 0 now. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 17, 18. And now if I do 100 to 199, this will be we keep this number on the left. Yeah, but then inconveniently we want to shift all of these numbers up, which we would need to do with some kind of text editing. Yeah, we need to be able to code this kind of switch. Or we need column pasting. Ah, interesting. Column pasting. Yeah, actually, we've run across many cases where column pasting would be beneficial. I want to be able to column pasting, also column selection. I want to copy everything that's within this block of columns. And then to be able to paste that into columns. Actually, I wonder if just the phrase column pasting, neo-vim column pasting. No, that's not going to work. How do I paste a different column of text? Specifically Vim, though now that I'm thinking about it, if you could copy and paste, let me see. Can I copy and paste this? If I try to paste that. Interesting. Okay, so now I need to know spreadsheet coding. Yeah, just do 0. I know what it means. Alright. So I can copy this. Right, now the next column is 1 through 18. Now, can I functionally add 1? Did that? No. Let me see here. How do I apply it? It seems like that would be one of the easier things to accomplish. Really? Okay. Adding a number to the column. Cell would be better. I've stopped having fun. I am no longer having fun. On the other hand, I'm not going to submit an open form solution when a closed form clearly exists. So I don't want to go back to coding until we've resolved this. But this is a useful tool for now using Dr. Racket, since we can't, like, I'd have to retype everything here if we can't figure out how to do this with columns here. Alright, let's reread this. Alright, so I enter a number here. And now here I say equals B19 plus 1. Okay, and now I drag that down. That is correct. Okay. Uh-huh. I see. Okay, and if I instead make this, so let's do if I say equals 1 plus 1, and I try to drag that down. Yeah. Yeah, you want to be able to say this cell. Let's see. Okay, let's try that. No, we'd have to get an example of that. What if I, guessing and checking is not it's a good way of doing this, but I guess cell equals cell R0 colon 0 plus 1. Okay. That is not correct. Can't guess. Nope. Let's see. What if I do? Reference. Is there an alternative way of doing this? So if I did like 2 and then I said no. If I did yeah, well, this is like trying to guess and check a programming language. It's not going to work out so well. Yeah, well, it shouldn't be. Well, I don't know. Should my spreadsheet not have the accessibility? The accessibility to. This is only formatting, otherwise this would be useful. Yeah, this killed any momentum I had behind this thinking. To get to the thought, this is going to shift up, so this is 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 10, What's wrong? It keeps increasing, right? And then we could do ... 900 through 999. And now same formatting, except now this should be 27. I think. Should be a note that tells me that somewhere around here. Well, the idea would be this is 0 to 99, and then we have to add 9 because we're going up to 900. Ideally, that's the rule, though the number of off by 1 problems I've encountered in my life says that that's not going to be the case. Okay, I need... I need another copy of 0. What does F1 do? When do I use F1? Nope, I don't use F1 for that. Do I ever rebind F1 to 0? I would otherwise bind it to tilde, but I need that for backspace. Alright, let's see if... Well, okay, if I... Yeah, but I mean, I already can't use... So I have Shift F1 bound to... I have Shift F bound to mute, but I already can't use it because F1 here pulls up Racket documentation. So if I have Racket open, I'm flashbanging myself. So we could rebind F1 to 0, and the point is that when I get to 1 at the end of the number sequence, I can hit F1. I like it. Let's see if I regret this at any point. Remap a key. Okay. Let's see. F1. Okay, and we're going to rebind that to 0. Send text 0. Okay. Actually, that would also be a way of doing Shift F1 would then be a way of doing if I don't send text but I send this key. Whoops. Oh, cancel. I don't know what that setting does. Select F1. If I send key, we can use this for close parent. Shift F1. Interesting. And then Shift F2 we could also rebind and have that be okay, and we'll have that be but then that would be open parent. We'd have the parents reversed. Yeah, never mind. We can get away with maybe just close for now. Alright, so what does that do now? Apparently not. Okay, let me see. It might be... I don't think it's because I have this open. Hold on. Remap. Okay, apparently it didn't register. Probably didn't hit OK. Alright. Continue anyway. Alright. Now F1. Alright. That's going to speed up my number entry. Okay. Supposing I can remember to use it.
and supposing we don't have any other uses for f1. And now I do want 19. Actually, yeah, I mean, really, if I could get 7, 8, and 9, 6 is no problem. 7 I could probably get, but 8, 9, and 0 are out of reach. I have to guess, I have to jump for it, and that regularly fails. Alright. This was supposed to be an enlightening number theoretic investigation, and it turned into wrestling with spreadsheets and failing, losing. Oh well. So this tells us how many numbers have this sum in this range. Now, the desirable observation here that we want to be able to take away is that this sequence it's like, well, the number on the left, the numbers on the left stay the same. The numbers on the right increment by 1 for every 100. Actually, that remains true. That remains true as we continue forward into 1000, doesn't it? No, it resets at 1000. So if I do 1100, let me see here. 1000 to 1101. Well, you know, I don't like that. That throws off our question, doesn't it? Yes, well, in a way it doesn't, because we have... It just fills in the spot that would be 2. Uh-huh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I guess it's exercise time. Alright. Yeah, this is not a good way of doing it. We need to stay within functions because it's functions that extend our ability to change our outputs, control our outputs. I mean that here what I want is each number in this position to be const on or to be displayed alongside. But because I've laid it out like this instead of creating a function to do this, and then for that matter, also this is quite inefficient, but beyond that, because this isn't a function, I can't, as it were, with a flick of the wrist, update these values. Anyway, now, alright, exercise time. I have to go to the bank at some upcoming day, which, in the best case, is already a Kafkaesque nightmare. But the best case would be that I have a normal sleep schedule. I'm going in the middle of the day. Now instead I'm going to be going at the end of my day after I've been thinking for 12 hours straight. All my life, people have asked me questions where they think I think the answer is important. Or they've assumed that I think the answer is important. A lot of assumptions, not a lot of asking. How do you not have your social security number memorized? I don't even use it once a year. Why would I have it memorized? Everyone has it memorized. Why don't you have it memorized? Dig into my important document folder. Get out everything because who knows what they're going to ask me. What's your middle name? Why would I care? When do you think I use my middle name? When do you think that happens? Do you suppose? What is your name? What? Better yet, just ask me what my identifying number is, okay? Now, if the banker asks me, what is your opinion on the reality of mathematical objects? Well, now we can have a conversation. Is the idea of this as a fighting style, to the extent that it is one, I'm not saying it is one, but if I wanted to use this in a fight, am I going to try to make it like fighting molasses? What do I mean? Like, I grab your wrist. I grab both of your wrists. Okay, and you're like, ooh, and I'm like, nope, nope, nope. And then I just keep saying nope until they can't move their arms anymore. And then I put down their arms and I say, okay, now what? I don't think they're gonna let you do that. Though that would be the more amenable way for a fight to proceed, I think. don't know how long of a plank I can do, so I don't know how much time to reserve for it. But let's find out. Okay. Difficult to breathe. Not a good sign. Okay. I could go a little bit longer, but I don't want to force anything. It's taxing my legs more than my abs. Though then, good leg exercise, I suppose. It doesn't stress the knee either. Speaking of which, much. Okay, see you soon.